Welcome friends to my YouTube channel. Now on my last lecture I have just introduced the concept of Galilean transformation equation. Okay, and I derived the Galilean transformation equations by assuming the universal nature of time. Now in today's lecture I shall going to discuss another issue that is called Galilean invariance. Galilean invariance. Okay. Now, first of all, we have to see that length is invariant. Invariant under Galilean transformation. Length is invariant under Galilean transformation. So, how we can justify it? Now, suppose there is a rod of say length L. Say one end is at x1 and another end is x2 as observed from S frame. Okay. So for an observer in S frame, say one end of the rod is x1 and another end is x2. Okay. So similarly, for an observer in S dash frame, the length of the 2 points, that is two endpoints, will change. Suppose this is for an observer in S dash frame. Okay. Suppose this is for an observer in S dash frame. Now, for an observer in S frame, the endpoints of the rod are x1 and x2, and for an observer in H dash frame, the endpoints changes, that is x1 dash and x2 dash. And here H dash is moving with a uniform velocity v with respect to S frame. Okay, the frame S dash is moving with a uniform velocity v with respect to S frame. That means S dash is also inertial frame. Okay, because any frame that moves with a constant velocity relative to an inertial frame will also be inertial. So H dash is also inertial. Okay, so we can write in H dash frame this. Now we all know that x dash equals to x minus vt. So x2 dash means what? x2 minus v t2, and x1 dash means x1 minus v t1. Okay, so clearly x2 minus x1 minus v, this is t2 minus t1. Okay, and since the time is universal in Galilean transformation, that means t1 equal to t2 from the universal nature of time. That means if a clock in S frame will measure the same time as the time measured by another clock in S dash. So universal nature of time is absolute. So this term becomes 0. So the length of the rod becomes x2 minus x1. Okay, so x2 dash minus x1 dash becomes x2 minus x1. That means the length of the rod is invariant under Galilean transformation by assuming the absolute nature of time. Okay, so what we conclude from this? Now, length of the rod is invariant under Galilean transformation by assuming that time is absolute. So this we can conclude. Okay, so length of the rod is invariant. So let us come to another issue. Let us check whether velocity is invariant or not. Okay, so we know that x dashed is equals to x minus vt. This is the Galilean transformation equation for x coordinate when the frame s dash is moving with a constant velocity v with respect to s frame in positive x direction. So this is the equation. Now dx dash dt, what will be this? There is dx dt, and since v is constant, this is this. Now here we assume the universal nature of time, that is t dash equal to t. So what will be my dt dash dt? This is simply 1. Okay, and we can write dx dash dt this as dx dash dt dash into dt dash dt. So this is 1, that means dx dash dt means dx dash dt dash. So if we substitute that, so this becomes dx dash dt dash, this equals to dx dt minus v. So this is simply u dash, this is simply u minus v. So what is u? That is velocity of the particle relative to s frame, and u dash is velocity of the particle relative to s dash frame. So it is clear that u not equal to u dash. Okay, because there is a v term associated with, so u is not equal to u dash. So that means velocity is variant under Galilean transformation. Velocity is variant under Galilean transformation. Okay, so this is our second issue. So now we see that length is invariant but velocity is variant. Now let us check whether acceleration is invariant or not. Let us check whether acceleration is invariant or not. So okay, the third thing is that acceleration. Now previously we write u dash this equals to u minus v. Okay, v is a constant velocity. So what will be my du dash dt? This will be du dt, and since v is constant, dv dt is 0. Okay, now du dash dt we can write as du dash dt dash dt dash dt, and since time is universal, dt dash dt is 1. So if we put 1, then du dash dt means du dt. Okay, du dash dt means du dash dt dash. So this is, we can put du dash dt dash, this simply equals to du dt. Okay, so this is simply a dash, this is equals to a. So what is a? Acceleration of the particle relative to s frame, and a dash is what? Acceleration of the particle relative to s dash frame. So we see both are equal, that means here we must mention, that is time is absolute. Time is absolute. Okay, so acceleration is invariant under Galilean transformation. Okay, so acceleration is invariant under Galilean transformation. Okay, so now let us check whether linear momentum is invariant or not. That is the laws of conservation of linear momentum, that holds good or not. Okay, now if we consider two particles, say m1 and m2, if their initial velocities is u1 and u2 and final velocities are v1 v2, this is as measured from S frame. Okay, u1 and u2 are their initial velocities and v1 v2 are their final velocities relative to S frame. So in H dash frame these quantities will change, that is u1 dash u2 dash, this becomes v1 dash, this becomes v2 dash. Okay, so what we can write from the conservation of linear momentum for S frame, that is we can write m1 u1 plus m2 u2, this equals to m1 v1 plus m2 v2, that is in S frame. Now what we can write in H dash frame, that is simply m1 u1 dash plus m2 u2 dash, this is equals to m1 v1 dash plus m2 v2 dash. Okay, so let us check whether this law is invariant or not. Okay, now here we can use this expression. Now previously we say we find that u dash equals to u minus v. Okay, so by using this relation we can write u equals to u dash plus v. From here we can write this. Now by using this relation we can write u1 this equals to u1 dash plus v, u2 this equals to u2 dash plus v, v1 this equals to v1 dash plus v, and v2 this equals to v2 dash plus v. What is v? Velocity of the H dash frame relative to S frame. Okay, here v is also that quantity. Now since we take two velocities before and after collision, these all can be written in this form by using this equation. Okay, so what we write in H dash frame, S frame, that is m1 u1 plus m2 u2, this is equals to m1 v1 plus m2 v2, that is the law of conservation in S frame. So here we can put u1 means u1 dash plus v, u2 means u2 dash plus v, v1 means v1 dash plus v, and v2 means v2 dash plus v. Okay, so simply m1 u1 dash plus m1 v plus m2 u2 dash plus m2 v, this equals to m1 v1 dash plus m1 v plus m2 v2 dash plus m2 v. So m2 v cancels, m1 v also cancels. So what we get, m1 u1 dash plus m2 u2 dash, this equals to m1 v1 dash plus m2 v2 dash. So starting from the laws of conservation of linear momentum in S frame, we arrive at the result of law of conservation of linear momentum in S dash frame. Okay, by using this relation. Okay, so we can conclude that the laws of conservation of linear momentum is also invariant under Galilean transformation. Okay, so what we conclude, what we make a conclusion, that is laws of conservation of linear momentum is invariant under Galilean transformation. Okay, so thus we see, what we see from today's lecture, that is first we see that length, this is invariant, velocity we see that it is variant, acceleration, this we see invariant, a conservation of linear momentum, conservation of say p, that is also invariant. Okay, so this is what up to today. Now in our next lecture I shall going to discuss the invariance of energy conservation. Okay, and then we move towards the rotational motion of frames. Okay, so if you don't subscribe my channel, then kindly subscribe it to get latest videos on physics. And if you have any query, then just write it in comment section. I will be ready to give the answers. Okay, thank you.